Hi everyone, welcome to this M2D2 talk. Our speaker today is Gabriele Corso, and he is a third-year PhD student at MIT in the laboratory advised by Tommy Yakola and Regina Basile. His research focused mainly on geometry deep learning and generative model and the application to the challenging problem of biochemistry and physics in drug discovery. Thank you so much, Gabriele, for accepting to present your work to this group today. And yeah, without further ado, the floor is yours. And for the audience, if you have any question while Gabriele speaks, please raise your hand or write in the chat, and he'll be more than happy to pose and take the question when he has the time. I think you are still on mute, Gabriele.
Okay. Yeah, thanks. Thanks so much for the intro, and thanks to you and Dom for the invitation. Very happy to be talking here today. So we're going to be presenting particle guidance. We're going to be talking about how we can sample diverse elements with diffusion models. This is joint work with Yilun, Regina, and Tommy from MIT, and Valentin, who was at EarnS and is now at DeepMind. And yeah, as Prudential mentioned, feel free to interrupt me as we go. Happy to take questions at any time. And let's get into it. Okay, so with most generative model, we focus on I.I.D sampling. And so the way why this is that with generative models, we're typically trying to learn to sample from some data distribution P. However, at inference time, when we actually use these models, we use them to sample a number of elements, or more than one, to represent this distribution. And so we would typically want these samples to be diverse and representative of our distribution. You know, let's say the different conformers for a molecule, or different images for a text prompt. You know, here I have the images for the text prompt Van Gogh Cafe Terrace. And, you know, for example, you can see, you know, DALL-E, the images are pretty similar, you know, obviously inspired by Van Gogh painting, but similarly also for stable diffusion. Some of them are almost duplicates from one another. While we would want these samples that we generate to be, you know, diverse and to be representative of their whole overall distribution. And, you know, why is I.I.D sampling not efficient? So first of all, for those that are not familiar, I.I.D sampling just means basically taking independent samples from the same distribution. So we said we train a model, let's say, you know, diffusion model or some other model to generate sample from some distribution. And then we apply this model independently multiple times to obtain multiple samples. And so let's apply this to this very simple setting that we will see of this 2D Gaussian mixture of Gaussian distribution, where we have these 10 Gaussians around the circle. And so we're going to take 10 samples from this distribution. And so if we take samples I.I.D, this is an example, we actually gonna, you know, basically take several of these samples to be in the same mode of another sample. And so while we could, you know, with 10 samples, you would probably want to actually discover all these modes, but instead you're actually gonna focus, you know, you're gonna end up sampling the same modes multiple times. And we can see here, you know, in expectation, the number of modes captured with the number of samples. If we have n samples, and, you know, let's see here, for example, is with 1,000 modes, and, you know, we have 1,000 samples, we're going to sample on average, you know, 65% of the modes, while we could be optimally sampling all of the modes. And, you know, in statistics, this phenomenon is well known and has been studied beyond, you know, these very simple combinatorial examples. Something called antithetic sampling basically looks at the way that we can reduce Monte Carlo estimates of some distribution by sampling diverse set of points. Similarly, there's something called determinantal point processes that sample diverse set of points. Even in molecular simulations, it is also pretty well known. So the most common method here, or one of the most common methods, is couple replica, where instead of sampling one particle, one element or like structure, depending on the kind of molecular simulation you're running, we sample n of them in parallel. And so instead of sampling from the independent distribution, we add this joint potential and then try to basically sample an element proportional to this joint potential. And since this molecular simulation basically work, if you're not familiar with them, like energy-based models, so where you're taking samples depending on the energy, you can very easily add this potential to your original potential and follow this overall joint potential. Similarly, there is the method called metadynamics, where instead of sampling n particles in parallel, we sample them sequentially, one after the other, but changing what's called the Hamiltonian, that you can think about as the energy function, in a way that will push the new particles away from previously sampled ones. And so this is an animation of metadynamics. And you can see that basically as we sample more and more particles, all from the same modes, we are kind of now filling these modes. And so we are going to be able to sample also different modes and the transition paths. And so kind of putting these two together, we can see that controlling joint distribution is relatively easy with energy-based models. But the problem is that, and I'll kind of get back to this, these energy-based models have been seen before to lack exploration. This is kind of why we use diffusion model, for example, to generate conformers or images. And so then the question becomes, can we use similar ideas to sample diverse set of elements with diffusion models? And so let me give you a quick introduction. I'm sure most of you are familiar with what I mean by energy-based model and what I mean by diffusion model, but let me give you a very quick intro. So in diffusion models, we want to sample from some data distribution, which I'm representing here by this 2D data distribution. And so the way that we do this is that we define a forward process, which basically noises the data and transforms it from the data distribution to a large, in this case, Gaussian. And then I'm going to learn the score of this evolving time distribution. So this is, the score is the gradient of the log likelihood. And so this is a time evolving vector field. And then we use some property that was actually proven in the 80s, but rediscovered by the diffusion modeling community recently, that we can basically reverse this diffusion process following this SDE, a reverse SDE, where in addition to F and G that we had access when we kind of defined this forward diffusion, we only need the score that we learned to approximate with our neural network. And so we can start from samples from our prior distribution, and we'll end up with samples of the data distribution at time 0. And so the critical part here is that basically diffusion models, by adding this smoothing function in a sort of like quote unquote finite number of steps, finite number of time, converge a point from the prior distribution to the learned data distribution. And so this is the big difference with something like energy-based model, which instead only operate on the energy of the data distribution. And so these often have issues with, for example, the fact that they get stuck in modes based on particular initialization. And in general, I have no finite time guarantees in terms of sampling from the data distribution. If the modes, for example, are separated, it's going to be very hard for the model to discover a new mode. And so, we want to basically take the disadvantages that we have seen over and over with diffusion models, but at the same time combine it with what we've seen before about improving kind of diversity in a way that we've seen done with energy-based models. And so this is kind of the motivation for the framework, the general framework of particle guidance, which we analyze in this paper. And so we modify, instead of now having our reverse diffusion process, just basically following this reverse SDE with the score, we now have this particle guidance term in addition to the score term. And you might be familiar with guidance used in the setting of conditional image generation, for example. And even there, we are kind of using a quote-unquote guidance term from some probability distribution. But here, the big difference is that we now have a set of elements that a set of particles that we are sampling in parallel. And so this is kind of what's represented by the I here. So this is the I particle. And this guidance term not only depends on the position of the I particle, but depends on all these positions. And so the effect here, looking from these examples from this particular initialization of some point in the diffusion process where we have these three samples that we are taking represented by the crosses. And so with diffusion model, we would basically be following the score given by the blue arrow. But with particle guidance, we also have this additional term given by the red arrow that's basically pushing away kind of different elements from one another. If we are trying, for example, to improve diversity, I have this kind of guidances for different things, but here we're improving diversity. And so the effect is going to be that you combine kind of like the direction from your score model with this enhancement of diversity from the particle guidance. Prudential?
Yes, I think I've missed that, but what's n here is the total number of particles you are sampling n point at the same time, or those are the n previous point that you have sampled?
Yeah, so we are sampling in a parallel. So in this sense, it's more similar to, for example, to couple replicas. So here n would be equals to 3. So we are sampling, 3 points in parallel, or we are sampling like 4 images for like stable diffusion, or we're sampling a number of conformers in parallel. And so we are sampling a number of points in parallel. And so, xi is one of these n elements. And so basically every step in our diffusion, all the particles are not only kind of influenced by the score at their point, but also by this joint distribution that depends on the position of the other particles.
Okay, and is it possible here to consider, let's say I have already some point generated before, in the new generation, consider them to make my new sample very diverse from those ones?
Yeah, you can definitely add that. This is something that we consider, but we actually didn't end up adding some experiments in the paper. But you can basically, consider them as virtual particles, where you are basically, repelling from these particles, and you wouldn't take, obviously, since they are already sampled, wouldn't move those particles, but it would basically push all the other particles away from the ones you have previously sampled.
Perfect, thank you.
And so two things.
Sorry, what is this? I don't know how to pronounce it. F, like Greek F, capital. What?
Phi.
Yeah, phi. Yeah. Mm-hmm.
So phi, we will see you can see it as a joint potential. So for example, and we will see kind of different ways that we can initialize it. So one thing to notice is that it's a time evolving potential. And one way that you can think about this is that if this is a measure of, let's say that we want to sample diverse set of particles, which is mainly what we're going to focus on in this paper. Let's say that this is log phi is a measure of diversity. And so at every step, you basically are trying to increase, you're taking a step in the direction that increases your measure of diversity. And so this it's a time evolving potential that is sort of, for example, encodes diversity. And we will see how we can, either set or learn phi in a way that optimizes different properties.
Thank you.
Okay, so a couple of things that I want to quickly highlight is that we are actually still using the score model, so we don't need to relearn the score model, but we can use it as an add-on. And depending on phi t, this can be very lightweight, and we will see different ways that we can choose phi t with different properties. And so, before going into the actual instantiation, I want to actually draw a few interesting connections with some of the existing tools in other fields. So the first one is Stein variational gradient descent, or SVGD, which is a very common method in variational inference, where you start from a set of points, a set of particles, and then you iteratively transport and iteratively update them to basically match a distribution. And you have these iterative updates where every step you're taking, you have some similarity kernel K, and then you're basically taking one step in the kind of direction that decreases this similarity, and one step in the direction that sort of like increases your the amount that you represent the data. You can see this kind of score term this way. And under specific choices of drift and potential, which I guess aren't necessarily the ones that we are going to use in the experiments. However, you can actually see the ODE discretization of particle guidance as being approximated by this, and you can clearly see some similarity between SVGD and this particular instantiation of particle guidance, where you have this repulsion term in both cases, and then you have this smoothed out score. So in the case of diffusion model, obviously the smoothing comes from the fact that we are using the forward process, and that's kind of how we smooth the score. While in the case of SVGD, the way that actually the score is smoothed is by basically taking a weighted average of the score at the nearby basically particles. And so you can sort of see SVGD as sort of like running a sort of like diffusion model with particle guidance. And so something interesting is actually this is sort of like a different interpretation of SVGD, and maybe this actually can provide more new ways to actually study its several issues, for example, mode collapse that we often see, and the fact that it's very hard to obtain with SVGD any finite time or finite particle convergence guarantees. Another interesting connection that one can draw is with electrostatics. So here, you might have heard of the Poisson flow generative model developed by Yilin Xu and others at MIT. And so basically what they did is that they define a new kind of generative model that instead of being based on a diffusion process, it's based on the evolution of point charges in an electric field, where the electric field is sort of generated by the data points. And so something that becomes natural is that if you now consider a set of particles in the same electric field, now these particles are going to interact with one another. And so what does this evolution actually correspond to? And something that we show is that you can actually see this evolution as being a combination of PFGM and particle guidance with a particular potential function. Okay, so these are some of the kind of interesting connections with other fields, but let's get into the more details of the way that we actually use and instantiate particle guidance. And so we are going to look at two different sort of like flavors. The first is using some fixed potentials. So here we are using some handcrafted, basically, potentials that require no further training and have, we'll see, kind of little inference overhead and very good empirical performance. But then there is the question of, okay, what kind of theoretical guarantees can we get out of this about the joint distribution and about the optimal amount of diversity? And this is where the learned potential particle guidance comes in, where, to obtain optimality, you actually need to learn a data-dependent potential. And so we provide ways of actually tractably training this potential and showing that you can get, optimal, diversity, and you can also control for something like a marginal distribution. So let's first dive into the sort of fixed potential. So here, as I mentioned, we use handcrafted potential where, no further training is needed. This is really like an inference time addition. And so for diversity, the easiest kind of potential that you can add, and this is what we do, is adding sums of pairwise similarity kernels. And obviously, since we want to have a diversity objective, we will look at the opposite of this. And so here, Kate's a similarity kernel. We'll typically be using an RBF, what's called an RBF kernel, which is the exponential of the negative of the distance between the 2 points. And this alpha is just, a hyperparameter. And so fitting this in the previous SDE that we saw, we obtained something where you can, again, kind of recognize the score term and the particle guidance term. And here it's very clear, this term is sort of like trying to match the distribution. This term is trying to improve and force diversity. And as we will see, it's important to make domain-dependent choices on what kernel you would want to use to reflect the diversity that you're interested in. And this is something that's going to become clear in the empirical experiments that we'll see. Now, one might ask, for an arbitrary, time-evolving potential, what is the resulting joint distribution? And so here we obtain a formula for basically the reweighting factor that particle guidance using this time-evolving potential induces on the original independent distribution. However, basically, this is very hard to work with arbitrary potentials. And now this is not necessarily a problem because for, I would say, for most domains, you are actually not, it's not really a necessity to exactly control the joint distribution that you're sampling. You just want to increase, for example, the level of diversity of your sample in general across some dimensions. But as we will see towards the end, for some domains, you might want to actually be controlling the resulting joint distribution. And this is something that you'll need to learn a specific time-evolving potential for. So before we get into the real experiments, let me kind of get back to this mixture of Gaussian experiments to give you a better intuition about some of these things. So again, here we have a mixture of 10 small Gaussians in 2D. And then we take 10 samples. And we are looking at how many modes do we recover with these 10 samples. So basically, recovering a mode means just having at least one sample that's in that mode. And if we do I.I.D sampling, so if we just sample 10 times from our diffusion model, generative model, we obtain an average the recovery of 6.5 modes. And if we use particle guidance with an RBF Euclidean kernel, so here RBF, so the kernel will be the exponential of minus of the squared Euclidean distance. We obtain, on average, the recovery of 9 modes. So we significantly increase the number of modes that we can recover with 10 samples. But we can also, in this particular case, for example, note that all these modes actually lie on sort of like a radial circle, center here in the middle. And so if we add the radial kernel centered here, so where basically the kernel is basically just the difference of the angle of basically the angle between these two particles, again, with an RBF, we actually obtain the fact that we always are able to recover all 10 samples. So all 10 modes. Yes, Prudencio?
Yes, in practice, you don't know the number of modes. And so how do you choose what kernel to use to kind of guide the sampling?
Yeah. So here, like the number of modes, here it's really the number of particles that you're sampling, and the number of particles really depend on your distribution. Kind of here, obviously, we've set the number of particles to be equal to the number of modes, but that's not necessarily the case in practice. This is kind of like a synthetic experiment, but even as I kind of showed in the earlier slide, even if you are taking 8 samples, the number of modes that you recover with I.I.D. are still very suboptimal from the ones that you could recover with 8 samples, and similarly with 12, 15 samples. So this is really like a factor of how many in your particular application, how many samples are you interested in taking. And point number 2 is the fact that the way that you can choose basically this kernel. You ask basically how do we choose this kernel? And one of the clear thing that we can do, and we can see in the in maybe some of the more real experiments, is basically this is really becomes like an inference time procedure. So basically you can try different kernels, and then you can evaluate does this improve my my metrics that I'm interested in. And that's a very simple thing to test, because it's really just an inference time addition in this case.
Okay, perfect. Thank you.
And so, yeah, let's look at some real experiments. And so the first set of experiments we will see is applying this to stable diffusion. So I'm sure most of you are familiar with stable diffusion. This is text to image generation. And so the way that stable diffusion works is uses particle guidance. And this particle guidance, what happens is that you have a sort of a weight that you use to give to your particle guidance classifier. Classifier guidance, not particle guidance. And the more you increase this weight that you give to the classifier guidance, the more you increase the fidelity, but this comes at the expense of diversity. And so in particular, we test particle guidance with 2 different kernels, basically an RBF kernel in latent space. So this is sort of like, you can sort of see this as a pixel space, not really the pixel space, because latent diffusion operates on this kind of somewhat lower dimensional latent space. Or we also apply this in feature space using the Dino featureization. And then we vary the classifier guidance weights to visualize the trade-off between diversity and quality. And we basically, what we can see is that basically particle guidance is able to push the Pareto frontier of quality versus diversity. And so typically you would choose this classifier guidance weights in a way that it's still it's as good as possible while maintaining a good enough amount of diversity. And so here we are basically pushing the Pareto frontier of how good of samples you can take. And so these are some of the qualitative experiments. And to look at some more qualitative experiments, we can make a couple of observations. So the first one, we use some of the prompt proposed by Somepalli et al. In this paper, where they analyze the memorization issue with stable diffusion and these other text-to-image generation, where they are kind of like, they show that this basically a lot of the times are spitting out just the training data. And so you can see this happening here, with I.I.D sampling, with this prompt, you basically 2 of the 4 are basically a copy of the original painting in the training data. And when we apply particle guidance, and to note, this is using the same using the ODE and the same random seed. So if you just run it with no guidance, you would basically obtain the same images. But you can see that now only one of the images resembles the training data, and the other one it's very different. And if we do as Prudential you'd suggest of actually adding this pushing away from this training data, we would again obtain 4 different images, all different from the training data. But if we are trying to improve diversity, you can see here we really have no duplicates, while here we tend to have duplicates. Another kind of observation that we can see in general, and this is a prompt from Coco. This is actually the first prompt that one of our reviewers asked us to do. And so this is a baby eating a cake with a tie around his neck and blah, blah, blah. And so you can see I.I.D sampling, you get, babies that, have all the same type of hair, all the same skin color, et cetera, et cetera. So not a lot of diversity, even though there is some, general diversity in the setting. And while when we add particle guidance in feature space, we can actually see that we obtain a definitely more diverse set of, for example, hair color, skin color, et cetera, et cetera. And so, one could even think about, adding, these particle guidance potential across, different feature that one is interested in increasing the diversity of, let's say ethnicity or so on, and this would sort of like give that effect. So now we move to the second set of experiments. So this is molecular conformer generation. And so here, so basically for those non-familiar, molecules have a set of 3D conformations that they take in space. And sort of these are the sort of minima of their Boltzmann distribution. And typically these are pretty deep minima. And so kind of the task of molecular conformer generation is really trying to find these different modes, trying to recover all these different modes. But in particular, we are typically never really interested in just finding one mode, but we're typically interested in recovering all the modes of this distribution. And so there's been actually a lot of development in generative models for molecular conformer generation. But interestingly, these all rely on I.I.D sampling. And so, typically the metrics are, based on, how well do you recover the original set? And the way that these existing methods do it is basically they train to generate an arbitrary element of the set, and then they generate a lot of conformers and try to hope that these conformers sort of like fully cover the set. And this was actually the original motivation for this paper. The fact that I.I.D sampling seems pretty inefficient in this case. And so we apply particle guidance on top of torsional diffusion, which again is a work from our lab that is currently sort of like the state of the art in molecular conformer generation. And so torsional diffusion operates a diffusion process over torsion angles of the molecules. And so we also apply the RBF kernel on torsion angle differences between different conformers. And this is also has a nice property that is relatively low dimensional and so more effective from a kernel perspective. And so we kind of compare with the existing methods on these geom drugs, which is the standard benchmarks, and we use this coverage, recall, and precision, which are the standard metrics that are used for this task. And we can see that for these metrics, there's always a trade-off between your what's called the recall, which is sort of like how well you cover the whole distribution of conformers, and the precision, which is for each of your of the things you generate, how accurate it is. And so there is always a trade-off between these two, and we can see that we can push basically the coverage versus precision trade-off, and this comes basically without any retraining, and so you can see these improvements over the vanilla torsional diffusion that uses I.I.D sampling. Okay, so here was the component on kind of this fixed, handcrafted potentials, particle guidance. And so if there are any questions on maybe the experiments and so on, I would take those before moving to the next component that's more focusing on kind of theoretical results that we can get with learned potentials. I see there are a few raised hands, Dominique.
Hey, so for your method here, are you basing it on top of torsion diffusion, or yeah?
Yeah, I'm literally taking the pre-trained torsional diffusion, and basically at inference time, just adding this particle guidance and kernel, and basically seeing how it improves the inference results.
Yeah. So what does it mean? Like the fact that recall has barely changed, but precision has changed a lot.
Yeah.
Like if I'm not mistaken, like the fact that you can sample a more diverse subset, in my opinion, would mean that recall would be higher, but precision would be lower because you're more explorative. But here we see the opposite.
So the way that this work is, unfortunately, you always have a trade-off. So for even particle guidance, you can sort of like it's always basically a trade-off between the two. So the reason, for example, in torsional diffusion, why recall is relatively high. I mean, one of them it's the fact that unlike it's basically the way that this benchmark has been set in the literature is that if you have n conformers, you generate 2n conformers, and so basically generate twice as many conformers. And so basically this is why typically this recall number is higher, basically because you are given kind of more sampling. And then the other fact is that basically because of optimizing the sampling, this for example, torsional diffusion is basically samples relatively, so like as a relatively wide distribution. And so this is kind of why it does pretty well in terms of recall, but then each of its samples, it's not really super precise because the distribution of samples is wider than if it's supposed to be. And one can improve this precision, but this would come by, for example, sort of like sampling at a lower temperature, but then this would kind of like create a trade-off with recall. And so basically the way that you should see it is really like a precision coverage trade-off. And so you have basically this Pareto frontier, and you can sort of like change this Pareto frontier. And unfortunately, people report these numbers in tables, and so it's very hard to basically show this Pareto frontier. But this is
Yeah, I guess showing the precision recall curve makes more sense. Okay, so here basically you've kind of optimized such that you keep about the same recall but maximize the precision. But you could have gotten higher recall by maintaining the same precision. Like that's what you want to say, right?
Yeah, so something like this. So I don't remember exactly this particular. In the paper, we have kind of both results. Kind of maximizing precision, maximizing recall. I think partially there is also like sort of like obviously there is a cap to which you can like maximize recall, because there are just some conformers are not torsional diffusion just doesn't cover some of the conformers, and so I think there is a relative plateau here in kind of what you can get, and so that's kind of one of the issues. But with this plateau, you can sort of like see that you can optimize significantly the precision while maintaining kind of the plateau level. I see Dennis has his hand raised.
Yes, hello. Thank you for the first part of the talk. So I have just two simple questions. The first one is, how many samples do we need to include in a batch for this to work? That's
a great question. So here, so it really depends on the number of samples that you're taking. But so for example, here for stable diffusion, since typically take 4 samples with stable diffusion, we use batches of 4. For conformer generation, since basically this varies, in this way this benchmark work is that it varies depending on the conformer of the molecule, the number of conformers of the molecule. And so the way that we actually do it in these results is that we basically take batches of, if the number of samples that we want to take is less than 128, we take that number, n equals that number. And if it's greater than 128, we divide in batches of 128. And the reason for doing this is partially kind of this, since I mean, this kernel is very fast, but it has quadratic, obviously, complexity because you're looking at all the pairwise kernels. So, if you have a very, very large batch size, then you get some cost in terms of computation. But actually, the biggest cost is that, like, if you're like when you compute the score, you have things in GPU memory, and so if you want to get a lot of samples in parallel, you have to take the samples in and out of GPU memory. And so what we do, one of the reasons why we use 128 is that 128 fits in the GPU memory for computing the score, and so we can just compute the guidance term across those without having to bring in and out of GPU memory these samples.
Thank you. That's clear. And two more questions. One is, again, I think simple. Just the initial, like, okay, you're running your kernel on each diffusion step. Like in SD, for example, it's just you're running once on each diffusion step, right?
Yeah.
Not like, okay. And do you find, how does it work when sort of the number of modes is greater than the number of samples between your inside your batch? So you would tend to get like non-overlapping results, right?
Yeah. So if your number of modes, obviously this sort of like this reasoning only makes sense if, for example, in the case of conformer generation, you have like relatively separate modes. But this is sort of like similar to the plot that I have here. So this is sort of like, this is optimal, this is not a specific method, and this is I.I.D. So you can see that if you are in the setting where the number of modes is much higher than the number of samples, then you're sort of like still quote unquote optimal, because it's unlikely that your samples are going to go on the same mode. while, once you become, around, in the same order of your number of modes, then this is kind of really where you have your inefficiency. And now, this being said, I guess one could argue this only sort of like works in kind of these combinatorial examples, because, one could argue that in the case of images, there are actually, this baby eating a cake with a tie around his neck, potentially, these are all different modes. They are all different images, but still you could argue that the diversity that it's in these pictures, especially along certain levels of diversity is relatively limited. And so that's kind of where this, combinatorial reasoning breaks down.
And perhaps for your learnable kernels, you can try to maybe navigate like particular features, particular subset of features to increase diversity. Although I'm not quite sure how to do it. But yeah, I have just one very simple question again. You start from many like initial samples from the prior distribution, from the Gaussian, right? So those are not like, okay. And what will, just from my understanding, if you will have a sampler that does not add noise during the generation, then if you do like exactly the same thing from the same seed, then this would not work, obviously, because the kernel would just return like infinity or something like that, or zero. So okay, and my last question is whether this is possible to apply with like flow matching techniques and so on, but maybe we will discuss it later.
To be honest, I haven't really thought too much about flow matching. I think it can, but that being said, it's still, I think, an open question, and I think a very interesting open question on what are the properties. So in the second part, we will see kind of, what kind of properties we can get when we kind of learn specific to preserve specific distributions. One could definitely apply a similar idea to flow matching. I think some of the theoretical results would differ, and I think it's an interesting question on kind of how this would translate to flow matching.
Okay, thank you.
Okay, so maybe in the interest of time, I'll go on the last part of the talk. I see there's still one raised hand, but I'll go on the last part of the talk, and then I'll take questions at the end, and I'm also happy to stay a bit longer than the hour, but I want to be mindful of everybody's time. So as I mentioned, with this fixed potential, we've seen some very nice empirical results. However, it's very hard to reason about the joint distribution that this model is learning, and in that sense, it's hard to argue about the global optimality of what we're doing. And so instead, here we look at learned potential particle guidance, where we see that by learning data dependent, so potentials that are really dependent on the probability distribution, we can argue something about the optimality, and we can control for different things. And a couple of notes, this is particularly useful in scientific applications, for example, where we want to do like something like importance sampling. So when we need to control for the likelihood of the samples. As we will see, it also allows us to control the marginal distributions. And finally, using something called the maximum entropy theorem, we can show that if log phi 0 is actually some diversity metric, this distribution that we are going to be sampling is actually the optimal in terms of maximizing that diversity metric under some bound on the KL of the joint independent distribution. And so still, however, the question is, while with the energy-based model, it was very easy to sample this joint density, just by adding this potential to our data distributions. Here, it's not easy because we have this time evolving vector field of the score, and the way that the score evolves doesn't necessarily tell us, how this joint potential should evolve over time. And so the question is, how can we find a time evolving potential that samples exactly this distribution? And in particular, we would like this to still use the original score so that we don't have to retrain a new score model. And so to achieve this, we sort of we don't use what you would have in your normal forward process from this distribution or Stern-Uhlenbach process from this distribution, but instead we set the sequence of joint marginals to respect this distribution, and then we show that the potential that satisfies this evolution through particle guidance is the one that minimizes this objective function. And so this objective function is particularly nice because these xi0 are all sampled from the independent probability distribution. So we don't need to sample this p tilde. These xt are samples from the forward kernel of our normal independent diffusion process, and then we have access to this phi 0, and so we are minimizing, and we are learning this phi t with parameters theta, and so we can find the parameters theta that minimize this objective function. One problem both with this joint distribution p tilde, but also with the fixed potential particle guidance, is that it doesn't preserve the marginal distribution of individual particles. And one clear example of seeing this is, again, this mixture of 2D Gaussian. So here it's a mixture of 2D Gaussian with this Gaussian in the center that's 4 times the weight. But you can see that when we are actually sampling the p tilde that comes from having this distribution with a Euclidean RBF kernel, because we are trying to optimize diversity, actually the model will give more weights to the modes on the outside, and much less weight on the modes in the middle, and in general will change the marginal distribution of each particle. So if you take each one of the samples and you marginalize over all the times that we're sampling, you wouldn't get this original distribution, but you would get something that looks like this. And the problem is that in some domains, preserving marginal distribution is important. For example, if we want to have correct approximate expectations and so on. And so the question is, how can we improve the preservation of marginals while still maximizing under this condition our diversity metric? And again, we can use the maximum entropy theorem, and we can show that this optimal distribution has the form where we still have our similarity kernel here as a potential, but now we also have this this gamma, which is a function of the individual particle that's sort of doing a reweighting depending on the position of the individual particle. And we propose an iterative scheme to learn gamma theta, and applying this iterative scheme to this particular example that I was showing earlier, we can see that we learn from theta some weights that are trying to basically put more weight in the middle mode and less weight in the side modes, especially on the side of the side modes. And then when we look at the marginal now, we can see that pretty much preserves the original marginal. And however, we can see that as we expected from our theoretical results in terms of maximizing the diversity, adding this condition is reducing the level of diversity by these metrics in the distribution, but at the same time it still has more diversity than the I.I.D sampling. So even if we want to preserve marginal distribution, we can still have more diversity than in our I.I.D sampling. And to conclude, before opening the floor to questions, so we've seen that I.I.D sampling is suboptimal for many settings where we want to take multiple samples from a generative model to represent some particular distribution. Particle guidance provides a framework to improve this diversity or other properties of joint sampling for any trained diffusion model. We show clear improvements in text-to-image and molecular conformal generation. In both cases, we are sort of like pushing this Pareto frontier of quality versus diversity, coverage versus precision, however you want to call it. And finally, in this last section, we've seen kind of our theoretical analysis leads to interesting results and training schemes. And we hope this can really be sort of like a stepping stone for further developments in this that we kind of believe it's a very important but largely unexplored field within the deep learning generative modeling community. And with this, thank you to you for listening and to my collaborators. Here are the links for the paper and the code, and I'm happy to take any further questions. Karim, I see you have a question.
So yeah, thank you for the talk. I wanted to ask, do you have any intuition on how the influence of the diversity term changes with differing levels of noise? So if you're at a high noise level or a low noise level, do you think that sort of influences the scale of the diversity that you're putting in?
So that's a good question. So to some extent, when you're doing it with fixed potentials, you sort of have to, this is something that you're basically controlling yourself. And so, for example, in our experiments, we have, this, even when what we call fixed potential, we mean fixed in terms of the it's handcrafted, but still, the kernel still is dependent on T. And so, similarly to the way that people do in other fields, we make this K to be, of similar size to the diversity between different samples at that level of noise. So this is one. But I do think that, depending on the kind of diversity that you're interested in, these are either diversity that, really come in at sort of like low noise levels in some settings, if you're interested, kind of maybe some fine grain diversity, or if you're interested at some larger scale diversity, this is going to come in at a different scale. And so I do think that, basically the way that, you measure diversity and the way that you, like diversity is something very vague, and, depending on kind of what you're interested in, the effect, kind of where in the diffusion model the effect should be, basically changes.
Thank you.
Dennis?
I think there's another, before Dennis goes, there's another question in the chat by Alec. Is there any connection to GFlow-Net that also improve diversity?
I guess not that I'm aware of, but I'm happy to, if you have some particular ideas on how this would apply to GFlow-Nets, this is not something that I thought about.
I think there's Emmanuel Bengio in the room. Maybe he can say a few words.
Okay. I mean, I guess GFlow-Nets are I.I.D samplers. So they still have this problem in some sense. One thing that has been tried though is to train GFlow-Net's condition on like the set of already sampled samples. And then the reward of the whole set is like based on some measure of mutual information between samples, or can be based on some diversity. But this has only been done on 2 examples, so I don't know, like the relationship here is a bit far-fetched.
Yeah, I wonder if, I mean, obviously, similarly, there could be a way that you would define, if you're sampling, a set of samples from a GFlow net, I imagine, you probably want to, somehow follow the flow in a way that, kind of is diverse. However, the fact that you have a DAG, it's obviously raises, challenging in the ways that, you could enforce, obviously you could force particles to go in different directions, but then maybe somehow you would need to define some way of similarity between different nodes of the GFlow nets in a way that encompasses the fact that in a DAG you can go back to particular positions. So I think there are some challenges.
Yeah, there's definitely a different approach. Like if there was a monotone-ish notion of diversity for like partially constructed objects, then yeah, this would work, but it's not always the case.
No, definitely. But I wonder if there is an approximate way of doing it based on maybe some embeddings of the DAG in some space. But yeah, it's definitely a challenging question.
Thank you, Emmanuel. Dennis?
Yes, thank you for the second great part of the talk. Honestly, my question is mostly just from the lack of understanding which I may feel by reading the paper, but regarding the time evolving potential, am I right that the objective function that you're learning is learned through, so it is learned on each step of the diffusion process, but it is not integrated through time, like through several diffusion steps, right?
Yeah, no.
I'm just, yes, I see. So essentially, what I'm confused a little bit about, if I understand correctly, you sample from the prior distribution from your noise, you calculate your kernel dissimilarity there, and then on each step you compare this with this kernel dissimilarity on the next step, and you just try to minimize this difference. This is a bit confusing to me because
it's a bit confusing, and I guess, I mean, the ultimate intuition comes from the proof. I would note that this is a particular setting where, for example, we are considering no drift in the diffusion process, so that might help to kind of explain. I mean, obviously with the drift, this would change. However, yes, I mean, I guess the intuition is that, like, you are sort of like at every step you're sort of like predicting the sort of like the final in the same way that sort of like with the score you're sort of like trying to minimize, like basically trying to figure out where you will get to at time zero. Here you're kind of like trying to predict at some point how much similarity you're going to get starting from this point at time zero. And so, in expectation over, time zero, this is basically what you learn, what you learn is correct. So the way that I would see it is basically this is trying to predict, how much similarity at time zero am I going to get from points.
Yeah, honestly, I am always always confusing. Time zero is noise or the data?
Time zero is the data.
Okay, yeah. Now this makes more sense. So this means that we need to. Then how do we obtain time zero?
Yeah, so time zero. Critically, these are samples from the independent data distribution. These are not samples from P tilde, but these are samples from the independent P. And so this is of this framework is that it uses samples at time P, not P tilde.
Okay, I understand. So and if on the contrary time zero would not be I.I.D, then this would not work. So here you're essentially, yes, you're sort of like bootstrapping yourself by the fact that you can take samples from your data itself.
Yeah, so this
and
is what you do during training, but what you would get during inference is disjoint distribution. So this is
Okay,
kind of,
yes.
it's different from, like just training a diffusion model over disjoint distribution. This is kind of where it differs. But yeah, so this is really sort of like in the first version of the paper, we really had it as a sort of like extension, then we sort of expanded. But I think this is where it's going to be very interesting for future works to follow up on kind of figuring out how the best way, or even empirically, to do this is.